Okay, in this lecture we are going to begin to transition from using the graphs to analyze motion. Still come back to that, it's a very useful tool. But we're going to start to explore how we could use functions or equations, so to speak, to solve problems analyzing motion. So we are going to, in this video, or I'm going to, I suppose, derive the kinematic equations of motion. Now, just FYI, you will not have to repeat this derivation. It's algebra based, it's not difficult, it's a little bit long. So this is not something where you're going to have to memorize all the steps and repeat this. I actually, this year, with everything being crazy the way it is, thought about even just throwing the equations at you and saying forget about it. But I just want you to see where they come from and hopefully understand that I'm not pulling them out of thin air. So the goal here is just for you to have a sense of where the equations come from, and then in class on Thursday we will start to practice using them together. So conceptually you need to have an understanding about what I'm doing right now. You might want to take notes and write down the algebra as I do it. But again, don't get anxious and think, oh my gosh, I'm going to have to memorize all of this. You will not. Okay, so when we're using the kinematic equations of motion, we are looking at something called uniformly accelerated motion, which is a very fancy way of saying we're looking at situations where the acceleration remains constant. So these equations that I'm going to start working with right now, they are only true or only work if the acceleration is constant. So anytime we have a constant acceleration, whether it's negative or positive, or I mean you could do it when it's zero, then this stuff will work. So in the guided notes I asked, so if we were discussing together in class, what would this look like on our motion graph? So if you had a velocity time graph, and I actually mentioned this in class on Monday. So if I'm measuring, looking at how velocity changes with respect to time, uniformly accelerated motion, constant motion, remember we're seeing that when we have a constant slope on these velocity time graphs. So anytime you have a straight line, it could be something like this, which is indicating a constant positive acceleration, right? Then you could use these equations I'm going to develop. You could use it if you have an acceleration of, this would be 0, where the slope is 0. So you could use the equations I'm about to develop. You could use it when you have a constant negative acceleration. The point is if your acceleration is changing, so if you would see a curve on this type of graph, then this stuff doesn't work. That's where you would need to use some things that would be developed in calculus to analyze the motion. Okay, so let's start the derivation. Now if you're following me in the guided notes, there's a table where I have 3 rows where we will list the 3 kinematic equations of motion and write down some things about each of those equations. I will do that at the very end of this video. So if you want to hold off on filling out that table until we get to the end, so you can make sure that you have what I want you to have written there. So we're going to come up with, there's actually technically 5 kinematic, oh, sorry, there's actually 5 kinematic equations of motion, but 2 of them we really don't use often, so I'm going to derive 3. And the 3 that I derive are going to come from 3 definitions, okay? So I'm going to start with the definition. The first definition is for average velocity. So average velocity, so measurable average velocity, is equal to, and I kind of mentioned this at the very beginning of the course last week, velocity is displacement, so change in position, this is how we write displacement, x minus x naught, divided by time, okay? So actually in your notes, in the first set of notes, you actually wrote down that definition already. So that's our definition for average velocity, and I say average because I mean over a measurable period of time. Remember when we were kind of mentioning in class yesterday, I think, the difference between instantaneous and average. So this average means I'm just looking at a velocity over a measurable period of time. So it would be my displacement divided by time. The second definition that we need to derive these equations is acceleration. Now acceleration is going to remain constant, so I'm not going to say average just because it's always going to be the same. But acceleration I defined actually earlier this week in class as well as being change in velocity divided by time. Remember the rate at which velocity changes. So v being that final velocity, v naught being the initial divided by time. So those two definitions are things we've already talked about. They should look familiar. The third definition is really just more a math-based statement. And it says that the average velocity is equal to the initial velocity plus the final velocity divided by 2. And this is true, so this is a way to find that average. This is true because the velocity is changing at a constant rate. Because we have a constant acceleration, so again, if you picture one of the straight lines on my velocity time graph, then we can say, well, your average value is just the initial plus the final divided by 2 to find that middle ground. Okay, so these are our three definitions, and from these three definitions, we are going to develop the kinematic equations of motion. So kind of what's happening here is we're taking these three things and we're just going to rework them. I'm just going to mess around with them a little bit to get them into equations that are more useful for us. So much easier in terms of approaching problem solving. That's the idea here, okay? So again, you're not going to have to repeat this process I'm about to get into, but I want you to see where these equations we're going to use all the time through the rest of the course, where they come from. Now, side note, I said there were 5 kinematic equations of motion earlier. The first equation I have here and the third are actually kinematic equations of motion as well. They're just not really practically useful in problem solving, so I don't feel like it's worth memorizing or whatever, but FYI, those are 2. Okay, so the first kinematic equation of motion is going to be really simple. We start with our second definition. A is equal to V minus V naught divided by T, and we just clean it up. So I don't even know if I call this a derivation. I'm just cleaning it up a little bit. Like, this is not pretty, this little fraction going on here. So I'm going to multiply both sides by T. So I'm going to say A times T is equal to V minus V naught. And then I'm going to move the V naught over, just to make it a little bit more approachable. So V is equal to V naught plus A times T. This, and I'll come back and rewrite it when we fill in that table at the end, as I mentioned, but this is my first kinematic equation of motion. V is equal to V naught plus A times T. So, just so I have space, I'm going to kind of erase, but I'll keep a tally of them over here. So there's my first one. V is equal to V naught plus A times T. Okay. The second and third one are a little bit more involved. So, the second kinematic equation of motion. If we look at our 3 definitions that are our starting point, we have a definition or a declaration of what average velocity is in my first equation. And then I say average velocity is something else in the second, or I'm sorry, the third definition. And so clearly, if average velocity is displacement divided by time, and if I'm saying average velocity is V naught plus V divided by 2, these two things must be equal to each other, right? Or else I'm lying to. So those two things we are going to set as equal to each other. So I'm going to say x minus x naught divided by t is equal to V naught plus V divided by 2. Now again, I just can do that because of how I defined average velocity. And I'm going to clean this up a little bit too because, again, lose the fractions. I'm not a fractions fan. So you can cross multiply. So you could say 2 times x minus x naught is equal to t times the quantity V naught plus V. Okay? And I'm actually, it's hard to explain why. Like, it's really just because somebody messed around with these things until they figured out a nice solution. so I know where they were going with it. I'm actually going to do a substitution from the third definition, so that being this one, the acceleration, the one that I did not use yet. And I'm actually going to use, you remember I reworked it in the beginning. I said v is equal to v naught plus a times t. I'm going to substitute that in right here for v. So this is, like, my math notation is so poor, by the way. I love math, but I'm not formal with it. So don't judge as I get going here substituting. I just like to draw arrows. Okay, so I declared earlier that v is equal to v naught plus a times t. I'm going to put that value in right here. So let me rewrite this line. 2 times x minus x naught is equal to t times v naught plus, and now let me put in my new value, v naught plus a times t. And I'm going to clean this thing up. Okay, so let's keep the left side the same, 2 times x minus x naught. And okay, so v naught plus v naught becomes 2v naught, right? And then we've got that t. So let's distribute that t in. So we've got 2v naught times t plus a t times t is a t squared. Again, I'm kind of flying through it a little bit because I'm not going to make you repeat it. And I've got 2 factors of 2, so I'm going to divide everything by 2. So I'm going to say, sorry, I'm running out of room. X minus x naught is equal to v naught t plus 1/2 a t squared. And that is my second kinematic equation of motion. X minus, this is the most commonly used one too. It's a really nice equation. It gives you a function for position with respect to time. So x minus x naught is equal to v naught t plus 1/2 a t squared. Now I'm going to write it this way like 98% of the time, of course, made up stat. But I'm going to write it this way almost all the time. FYI, if you see this equation other places, especially in a math class, especially the like 5 of you, I think was the number, whoever's in calculus, sometimes you see it written like this. It's the same equation. They've just taken that initial position and put it over here on the right side of the equation. Now this equation, it depends on the order you're doing your work in, but if you have started or finished that co-lab activity number 2 where you're sort of playing around with the position graphs, this was the equation that I was programming in there for you. Slightly different notation just because of the programming language, but this was the equation. Okay, so that's our second kinematic equation of motion. So obviously a little bit longer to get to, but I'm just, as you can see, just manipulating these 3 original definitions, okay? All right, let's get to the third kinematic equation of motion. So the third kinematic equation of motion starts at the same spot. Actually, I probably erased too much. Starts really in the same place. I'm going to use my 2 definitions for average velocity and set them equal to each other because they must be equal to each other. And I'm going to cross multiply. I should have left that line there. So I'm going to say 2 times x minus x naught is equal to t times v naught plus v. And I am going to take my third equation that I didn't use, this one. A is v minus v naught divided by t. Or I could have used it in this form that I've already changed. It doesn't matter. And I'm going to solve this thing for t and substitute it in there. So if I solve this for t, I can just rearrange this. So t is equal to v minus v naught divided by a. Again, I'm kind of skipping some steps on the algebra because I just want you to sort of follow along. And so this, again, just a rewrite of my definition for acceleration, and I'm going to take that and I'm going to substitute it with my fancy notation in for t in this equation. And so I'm going to say 2 times x minus x naught, the left side remains unchanged, is equal to t, which is v minus v naught divided by a, times v naught plus v. Now you know what I'm going to do is, I'm just going to switch these because this is addition and you can, and I'm like getting at a point here. So I'm going to write, instead of v naught plus v, I'm going to write v plus v naught, okay? And I don't like the fraction. I'm going to multiply both sides by a. So I'm going to say 2a times, sorry, my parentheses are always a little ugly. Also, I overuse parentheses like so much. I apologize. 2a times x minus x naught is equal to v minus v naught times v plus v naught. Now, from somewhere in your math life, maybe algebra 1, I don't know when you learn things, 8th grade, 7th grade, maybe 9th grade, this v minus v naught times v plus v naught, that's what we call a difference of squares, right? Hopefully that sounds familiar and brings back fond memories. And so I'm going to rewrite that side. So I'm going to leave the left side unchanged. I'm going to say 2a times x minus x naught is equal to the difference of squares. We'd say v squared minus v naught squared. And then the only thing I'm going to do, again, it's all about aesthetics with this equation now, just to make it prettier. I'm going to add, instead of having the negative sign here, I'm going to add v naught squared to both sides. So this equation becomes v squared is equal to v naught squared plus 2a times x minus x naught. And that lovely thing is my third kinematic equation of motion. Wasn't that fun? Now we're going to go back and fill out that table real quick, so don't hit stop yet. But there we go. So again, there's the like algebra all over the place. If you were an 8th grader and you walked into the room and saw this board, it might look a little bit intimidating, but hopefully, because you're not, you could at least, follow my process, right? Because this was all just algebra 1. Again, what I want you to pull out of this is that I stood here and I started with these 3 physical definitions, right? These are mathematical ways of stating 3 physical definitions. And I manipulated those 3 physical definitions to get these equations. So I didn't pull these equations out of thin air. They're just basically rewrites of these 3 definitions, okay? And I rewrote them again. Why? Because it's a lot easier to solve the problems based on what we can actually physically observe and measure on our Earth world in the rewritten form that I developed than they are to work with in this form, okay? So let's fill out the table and then we're done. We'll practice using these together. I want to talk about like problem solving and what I expect from you, etc. when we're actually face to face. So in the guided notes, there's a table. I'm doing this all off of memory, so I hope I'm getting these columns correct. There's a table, and kind of bear with me if I'm not. I think I put them in this order. I think I said like equation. And then the second column would have said something like, I forget the wording I used, like, I want you to talk about what this is like as a function. And this is really just a humor. We don't really care about it that much in physics. And then, like, variables included. And then variables left out. Hopefully, I've got the right word here. Okay, so there's my table. Clearly I'm super fancy with my board. Okay, so there we go. So the first equation, just to restate it, the first equation was V is equal to V naught plus A times T. V is equal to V naught plus A times T. So when I say function, what I'm saying is this tells me the final velocity of an object as a function of time. It tells me the final velocity of an object as a function of time. Variables included, I mean, like, seriously, what variables are in this equation? My final velocity is in that equation. My initial velocity is in that equation. My acceleration is in that equation. My time is in that equation. I'm going to leave this one until I get all 3. So we'll come back to the final column last. Okay, second kinematic equation. X minus x naught is equal to V naught T plus 1/2 A T squared. X minus x naught is equal to V naught T plus 1/2 A T squared. This is, as I mentioned, our most common, like in terms of function, this is our most common one to work with. And this gives me position as a function time. So this second equation goes hand in hand with my position time graphs. It gives me position as a function of time. If I graphed whatever with actual numbers, this equation, which is what you did in the co-lab activity 2, I am seeing my position time graphs. The first one, just to go back to that, v is equal to v naught plus a times t, that's giving me velocity as a function of time. If I were to graph this with some actual numbers, let's say I did some code, like I did with this thing, and let you manipulate the variables, you would be seeing the velocity time graphs, like that we've started to work with a little bit this week. So just FYI, they all connect in a lovely way. Variables that are included in this: position, so x and x naught, your displacement, the initial velocity, time is in there, and acceleration is in there. And then let's go to the third equation. So the third kinematic equation is v squared is equal to v naught squared plus 2a times x minus x naught. Now, as a function, I'll restate it just in case you can't read my handwriting. V squared is equal to v naught squared plus 2a times x minus x naught. So the function that this gives you is kind of a weird function. It's not one we work with in the same way as these two. But this would give me final velocity, final v, as a function of changing position, which is weird. And my handwriting is getting messier as I go. I apologize. Okay, final velocity as a function of changing position. It's not one that we really work with or graph much, so just FYI. But this equation we will use. We'll use that equation, just not graphically. Okay, so what variables are included? Final velocity is in there. Initial velocity is in there. What else is in there? A is in there. Acceleration is in there. And displacement. So I tend to write it as x minus x naught, just to keep it as one thing, displacement. But position, x and x naught are in there. Okay, so there we have it. There are our three kinematic equations of motion. Now, let's go to this variables left out, because you've got all these different things, right? So this first equation has my velocities, has my acceleration, has my time. It does not anywhere involve position or displacement. X minus x naught is left out of that first equation. The second equation has it. It has the x minus x naught, it has the initial velocity, it has the time, it has my acceleration. It is missing final velocity. Nowhere in that second equation is the final velocity. And then the third equation has the final velocity, has the initial velocity, has the acceleration, has my position stuff, my displacement. It is missing time. So the whole purpose really of coming up with these three equations is in certain physical situations, I might easily be able to measure, observe, quantify, like the time something is moving and where it started from in terms of its velocity, but I can't get position and I don't care about position. I just want to know how fast is it going at the end. This would be the appropriate equation to pick, right? So based on what you know and then what you want to find, you are going to choose one of these three equations which will best suit your needs. And to make that choice, you really have to think about which variables are left out of the equation. That might not make sense till we practice with it this week. So we'll definitely get much more into that concept. Now there are two variables that are included in all three equations. And those two variables are initial velocity. So you have to know, your starting point, essentially. How fast are you going to start? Rest, something backwards, something forwards. So you've got to know the initial condition, essentially, and acceleration. So these are constant acceleration problems. You have to know the value for that acceleration, or you have to know some of these other things and use it to solve for acceleration. So we'll certainly do that often, but it cannot be eliminated from the equation. So you see that it makes an appearance in all three. Okay, so I'm going to stop there. Hopefully this made some sense. Thanks for your patience in watching, and I will see you Thursday, and we'll just dive right into using these three equations.